Okay, welcome to lecture number 27. So, we have been discussing about Kepler's equation for hyperbola. So, already we did by one method. So, today and in the last lecture we have started with deriving with another method. So, the same method will continue and derive that, and thereafter we will look into various terminologies we have used and various equations used in these derivations. So, if you remember that we have written equation for hyperbola as x square by a square minus y square by b square equal to 1 in Cartesian coordinates, and then we stated that this is satisfied by a cos hyperbolic and y equal to b sin hyperbolic f. Okay, so, if we insert this, so we get here cos hyperbolic f minus sin hyperbolic f, this equal to 1, which is true, hence x and y described by a cos hyperbolic f and b y equal to b sin hyperbolic f, they lie on the hyperbola, and where the hyperbola we have shown as, so this is the center of the hyperbola, not directrix, and this is the hyperbola is shown, this distance we have magnitude wise we have shown it to be a, and if we draw a asymptote for this, so this is the asymptote for this hyperbola. So, on this side, if from here from the perigee, if we raise a perpendicular line, so it cuts here in somewhere. So, this is B and this is A. Similarly, on the this side also, in the last lecture I have shown that figure. So, again I am not drawing that the whole thing. So, this is the turn angle, this is the asymptote, and somewhere this is your focus, and this is the asymptote line parallel to asymptote, and this we have written as theta infinity, and this angle we have shown by beta. So, from this place if you look magnitude wise, this is tan beta equal to b by a. So, we will come to this particular figure again. Right now that is not required, and thereafter using this we have started writing by equation for the conic section, which is r equal to L by 1 plus E cos theta, and remember that L can be written as 1 minus E a square, and here this can be represented, or it can be written as L equal to a times C a square minus 1. In this case a is greater than 0, in this case a is less than 0, and we are stating it for hyperbola. Hyperbola for in basic definition for hyperbola a is taken as less than 0 for hyperbola, but if you write the equation in a particular way like this, so at that time you have to describe the semi major axis as a greater than 0. So, then using this equation we have written this as a times C a square minus 1 divided by 1 plus E cos theta, and then we rearranged it. Also y equal to r sin theta, and y from here this is available. So, this is b sin hyperbolic f, and this implies r equal to b sin theta, or let us write in the next step here. So, what we are going to do, what we have done, we have expressed sin hyperbolic in terms of theta angle or f in terms of theta angle. So, the same effort we are putting here. So, sin hyperbolic f this equal to y by b. From this place we can see this is y by b equal to r sin theta divided by b, and r is known from this place. So, a times e square minus 1 divided by 1 plus e cos theta and sin theta as we put here in this place. So, till this extent we have done this, and b is missing here. So, b again which we have not proved for the hyperbola yet, b equal to a times e square minus 1. Okay. This will be necessarily written in this way, e square minus 1, not 1 minus e square. So, here we have to also write a times e square minus 1 under root. Okay. So, this will get reduced to a cancels out, and here we have e square minus 1 under root sin theta divided by 1 plus e cos theta. So, this is sin hyperbolic equation we have got. Along the same line, cos hyperbolic f, this can be written as e plus cos theta divided by 1 plus e cos theta. So, this you can check yourself, this is left as an exercise. Okay, where we have used the fact that cos hyperbolic f square this equal to 1 plus sin hyperbolic square f. So, you can use this equation and you can get to this result. Okay. Thereafter, we wrote f equal to sin hyperbolic inverse and whatever we have written the terms here, this equation we have used it, e square minus 1 under root sin theta divided by 1 plus e cos theta, and this can also be written as this. Okay. So, there is one standard equation from text, you will get this sin hyperbolic inverse x, this can be written as this will prove later. For the time being, we take it for granted that this is written like this. So, this implies that here x is e square minus 1 under root sin theta divided by 1 plus e cos theta. Okay. And then we insert here in this equation. Okay. So, from there, so by inserting what we are getting here, this is nothing but f equal to sin hyperbolic inverse x. So, therefore, we get f equal to ln, and in bracket here the whole thing has to be copied, e square minus 1 sin theta plus 1 e cos theta, and then x square, of course, here e square minus 1 e square minus 1 under root sin theta divided by 1 plus e cos theta, this whole square, and then plus 1 and a square root of this whole thing. Now, this quantity can be expanded, and this particularly this inside the square root sign, this can be expanded and it can be written in a particular way. So, in that case you have x equal to x square plus 1 under root, this gets reduced to If you expand it and you can check it, few steps I am skipping here again because there is constraint on time. Okay, so the term under the square root sign is here and this term is copied here in this place. So, therefore, f equal to L E square minus 1 sin theta plus E cos theta divided by 1 plus E cos theta plus E divided by 1 plus E cos theta. So, this is the equation we are getting. Now, this has to be simplified. Okay. This needs to be simplified, and for that we need to do certain substitution. So, we will use this substitution sin theta equal to 2 tan theta by 2 divided by 1 plus tan square theta by 2 and cos theta equal to 1 minus tan square theta by 2 1 plus tan square theta by 2. So, this step again you can carry out, and if you insert this will get reduced to ln Okay, so it is not difficult to derive this particular equation. Now, we are going to the equation we have got this MH hyperbolic. This equation we have written earlier as, if you remember that by integrating this equation r square theta dot, so we rewrote it and thereafter we rearranged it to write it as and integrated it, and once we integrated it for hyperbola we got this equation. So, this we have written that this is a standard integration, this is an integration found in some standard textbook. Okay, so, this quantity this is cos theta minus E plus 1 under root tan theta by 2 this will be plus here and E plus 1 under root minus E minus 1 under root tan theta by 2. So, if you check now, so the quantity here written, this is nothing but f. So, this side becomes f, and what this quantity is, if you look here in this part. So, this part we have written earlier sin hyperbolic f, this is your this part. So, here we have E sin hyperbolic f minus f. So, we write here, and this is nothing but your Kepler's equation for hyperbola, which we have also obtained using, right in the beginning we have obtained using purely the mathematical method by differentiating, okay, where we were given this r and we use the equation for h square Okay, and then we differentiated this r, and we had the equation for h square. So, for combining these two, we obtained this m h. Therefore, we are getting the same equation by different methods, and it also verifies that whatever we are doing, it is a correct. Okay. So, there are few more things that we need to work out. Okay, particularly we have few relationship that we should look into. Tan E by 2, this quantity will be E minus 1 plus 1 under root tan theta by 2, and the same way it can also be written as tan theta by 2 equal to E plus 1 . Okay, so we will work on this also, but before that we need to do few more exercise. Okay, now let us look into the properties of the hyperbola. We have to get these equations. Already we have drawn this earlier. Asymptote is here. Asymptote is the line to which, say, if we have an exponential function. So, you can see that e to the power minus x, if I plot it, y equal to e to the power minus x. So, it will converge like this. So, the x axis is, let us say, asymptote. This is the asymptotic value, means as x tends to infinity, so you will see that y tends to 0. So, this is an asymptote to which this line becomes converges once r tends to infinity. So, already we have shown this to be, this distance to be b, this distance to be a, and this angle as delta. This part was remaining in our discussion. So, I am taking it up at this stage. Theta infinity, this angle we write as beta. So, we can see that beta equal to 180 minus theta infinity, because this is parallel to this asymptote. This is asymptote. This is asymptote. So, this is parallel, these two are parallel. Okay, so, we have b by a equal to tan beta equal to tan 180 minus theta infinity equal to minus tan theta infinity. This we can write as minus sin theta infinity divided by cos theta infinity. For hyperbola, we write r equal to 1 by, or for the conic section, e cos theta. Okay. In this equation, as r tends to infinity, 1 plus e cos theta then can be written as theta infinity. When r tends to infinity, this theta is referring to that. Okay, this is referring to this part. So, this becomes 0 and this implies cos theta infinity this equal to minus 1 by e. So, therefore, sin theta infinity this becomes 1 minus cos square theta infinity under root or 1 minus 1 by e square b by a can be written as sin theta which is e square minus 1 under root divided by e and then cos theta infinity which is minus and this gets reduced to e square minus 1 under root b equal to a times e square minus 1 under root. So, you have to also note that b will be always written in terms of b equal to e square minus 1 under root. You cannot write it like this 1 minus e square under root. This is only in the case of ellipse and this part is for the hyperbola. For hyperbola we always write it like this. So, we have got the expression for b here. So, these were few of the things which were left in the conic section and I told that we will cover while we discuss about the hyperbolic orbit. So, cos beta equal to cos 100 t minus theta infinity equal to minus cos theta infinity Now, going back into this figure, this angle is beta because this is the these two lines are asymptotes. This is the right part of the hyperbola and this is left part and distance from here to here this is r perigee and from this place to this place this is r apogee. So, cos beta is 1 by e and also we can see that 2 beta equal to or we can write delta the turn angle is equal to 180 minus 2 beta delta by 2 equal to 90 minus beta cos beta equal to 1 by e as derived above and therefore, delta by 2 this is sin inverse 1 by e or delta equal to 2 sin inverse 1 by e. So, these are the expression for r perigee and r apogee. So, you can see the notice the difference in the apogee and perigee location in the ellipse. Here this is the in the this case this is perigee here as shown by this red dot, while the apogee is shown by this blue dot here. So, these are on the two sides of the center and center is lying here which is shown by the yellow point. Center is lying in this point whose coordinate we have written as 0 0. So, there is a difference between the ellipse and hyperbola and accordingly some of the things change. Okay. And also if you notice we have shown that distance from the focus, okay, to any point on the hyperbola, say if we take point here on this and then we join the other focus. So, this is f, then this is f star, or we will show it by a small f, and if we write this as p. So, here p f magnitude minus p f star magnitude will be equal to 2a. This is the basic result. This is always constant. So, we will utilize this information. So, in the case if we look here at this point, so this is r apogee and this point is r perigee. On the blue dot I am putting a black dot and the red dot I am putting here a black dot. So, I hope it is visible. So, this is your apogee and this is perigee. So, if your p point coincides with this, it becomes easier to work out. So, let us look into this. So, at that time the r perigee and r apogee they are defined. So, 2a will write as r a minus r p. This is distance wise, okay, in that case. So, we have here r a equal to L by 1 minus c, but here remember that E for the hyperbola is greater than 1 and therefore, we will put a minus sign, because this L by 1 minus c, this becomes a negative quantity and therefore, we put a minus sign here and this is already a positive quantity. So, we write it this way. And if you rearrange it, so L can be taken outside, this is minus sign 1 minus c plus 1 by So, this is the semi-lattice rectum. But if you in this case then a is less than 0, but if you want to represent in terms of a greater than 0. So, the same thing you should write as here in this case this will be representing a greater than 0 and E also greater than 0. Here E is greater than 0. Therefore, this quantity this becomes negative . See, this part is little easier to handle, because you can remember that lattice rectum this will be given by a times c square minus 1, this is for hyperbola, and for parabola you are using a times 1 minus e square, this is for parabola. So, in the case of this parabolic equation, if we want to change sorry, this is for ellipse, this is for ellipse, and if we want to change it, so we have written as minus a e square minus 1. So, here we need to correct in this part, otherwise it will be confusing. So, we will follow this scheme. Here in this case, this a is, if we write it like this, so a is less than 0 in this part. If we write here in this way, so a is greater than 0. This is the expression for hyperbola. This is also the expression for hyperbola, but here in this case a is less than 0. So, this thing we have to take care of while writing, otherwise it may be confusing. So, this by this part we have rearranged, and this 2 cancels out, and a equal to minus L by 1 minus C square. This implies L equal to minus a times 1 minus E square, and once we rearrange, so this L equal to a times 1 E square minus 1. So, here in this case a is greater than 0 and also E is greater than 1. The format in which we are working, we are writing here, because this is the correction I have done, because this should be consistent with this. So, we have written in this particular format, and because of this the result we got it here this way, L equal to a times C square minus 1. Otherwise, you follow a standard form, which is the most standard one is this one. Okay, and based on this, in the beginning we have derived the Kepler's equation also, L equal to a times 1 minus C square. This is valid for ellipse, and if it is an hyperbola, so E will be greater than 1. So, in that case you will shift the sign outside. Okay, so, therefore, there is exchange of E square and 1. So, it gets into this form and minus sign comes outside. So, in this case we write a is less than 0. So, if we write a is less than 0, so this becomes hyperbola, and if we write a greater than 0, so here in this case if we write a greater than 0, so this case will be an ellipse. So, this is the most standard form, but many of the books they bring it to this form for their convenience maybe, but if we go by our basic concept. So, I will say that you follow this step and it will be the most convenient. Only thing that you have to keep care that B will be always defined in terms of B equal to a times E square minus 1. We never write it as B equal to a times 1 minus E square. This is not correct. Okay. This is only for the case of ellipse. This will be valid only for the case of ellipse, and this is for hyperbola. So, this difference you have to notice. Okay, so, some of the basic things we have already covered, and expressions also we have already written. Now, let us wind up this first. R equal to L by 1 plus E cos theta, we have used this earlier, which we are writing as a times C square minus 1. Again, this is non-standard format I am writing here. Otherwise, you can write it in the same way 1 minus C square, but there will be a minus sign outside in that case. Okay. So, specifically you should write a greater than 0 and E greater than 1 if you are expressing like this. Okay. Thereafter, we have we break this term a square minus 1 into two terms here, a square root, and the denominator we write sin theta and the numerator also we write sin theta. Okay. If we write it in this way, so this can be expressed as a square minus 1 sin theta, and this part if you remember, this is nothing but sin hyperbolic f as derived in the lecture, as derived earlier. Oh. We do one substitution here as we have done earlier also. So, E times 1 minus tan square theta by 2 1 plus tan square theta by 2, and then we need to rearrange it. So, now tan square theta by 2, if you remember, I have written the equation. I will also prove it here because this is required, but let us use that information whatever we have written earlier. So, this is the information I have used earlier, and this I will prove here, f by 2 e minus 1 tan hyperbolic square f by 2. Okay. This can be rearranged, and if we rearrange it, r equal to a times c square minus 1 divided by 1 plus okay. This part needs to be rearranged, and if we rearrange it, this can be simplified. This can be simplified to first simplify this part, cos hyperbolic square f by 2 minus e plus 1 sin hyperbolic square f by 2. The denominator will cancel out from the numerator. Here this part will cancel out. So, I am skipping one step and writing here and we need to rearrange this term again. E times E is one outside and inside also. So, this is E times cos hyperbolic square f by 2 minus sin hyperbolic square f by 2, and the other term comes with here only cos hyperbolic. So, this is cos hyperbolic square f divided by 2 minus sin hyperbolic square f by 2. and in the denominator we have the same way e cos hyperbolic square f by 2 plus sin hyperbolic square f by 2 and then plus or we can write even in terms of minus here minus cos hyperbolic square f by 2 and minus sin hyperbolic square f by 2. Here this is minus and cos hyperbolic minus sin it arises here. So, this becomes plus, it should come with a plus sign. So, going to the next step. Okay. So, r becomes a times e square minus 1 and then 1 plus e times this term needs to be simplified. You can see that this particular term here, this equal to 1 cos f square hyperbolic f minus sin f square hyperbolic f. So, this we write as 1. So, that becomes e, the first term becomes e. So, here you have e and thereafter this particular term is there cos hyperbolic f by 2 plus sin hyperbolic f by 2. So, this term we need to work out. Here also we have this particular term and this term equal to 1. Okay. So, this term is the right hand side is 1 and we need to work out. So, we will show that this is cos hyperbolic f and here cos hyperbolic f multiplied by e. So, we have here the last term we have written cos hyperbolic square f sin hyperbolic square f by 2. Okay, so, this term we have to rewrite it. So, we know that cos hyperbolic square f minus sin hyperbolic square f this equal to 1 or sin hyperbolic square f this will be cos hyperbolic square f minus 1. Okay, so, we can utilize this information here in this place. So, this term then becomes cos hyperbolic square f by 2 plus cos hyperbolic square f by 2 minus 1. So, that means this is 2 cos hyperbolic square f by 2 minus 1 which is nothing but cos hyperbolic f and which we have used here in this place. So, this term we are replacing by cos hyperbolic f. So, on the previous page this is your quantity cos hyperbolic f, this is cos hyperbolic f. But here with this e is multiplied and therefore, we have in this format and this is a minus sign here in this place. Okay. Once we have done this, rest of the steps it is not much difficult to work out. This cancels out and we get here a times e square minus 1 e cos hyperbolic f minus 1 divided by e square minus 1, and then this term and this term will cancel out, leaving us r equal to a times e cos hyperbolic f minus 1. Okay. So, you can notice the difference that earlier we have got here the expression a times 1 minus e cos hyperbolic f for r, but there then a was taken as less than 0. Here a is greater than 0. This is the difference, because this is the way we have expressed here. Here a is greater than 0, and therefore, in this expression a is greater than 0, and once we have proved our this Kepler's equation for hyperbola. So, at that time you remember that I have taken r equal to this. Okay. So, you can this difference always you should notice, because the different authors they will express in their own way, and I have presented here both the ways it can be done. Okay. So, this is the expression for r. Now, only thing we are left with proving this tan theta by 2 equal to e plus 1 e minus 1 under root tan hyperbolic f by 2, and this is similar to what we have got for the ellipse. In that case, here instead of f it was replaced by e. So, this particular part will work out, and before winding up the things, then what we will do, we will stop here and continue in the next lecture. Thank you very much.